Okay, everybody. So, what we're going to do today, new lesson.
Is it antiderivatives?
It is antiderivatives. In fact, actually, so basically what we're doing, everybody, listen up, okay, is we saw antiderivatives, okay, back at the, at kind of the tail end of the fall trimester. We briefly touched upon them for an AP question. What we're going to do today is go over them formally and basically do work with them. Okay, so we're looking at antiderivatives. And indefinite, excuse me. Integrals. Okay? So, this is what we're after. Antiderivatives are very much what they're, basically what it says. They are basically the opposite, or doing, not essentially the opposite. They're doing a derivative backward, okay, is what they are. And in fact, the actual definition of an antiderivative kind of assumes that. In fact, antiderivatives definition is basically a function, big F is an antiderivative of little f if on an interval big F prime of x is equal to little f of x, okay? Like so. And you can use that as your definition of an antiderivative. So, note here, defining what an antiderivative is, I'm basically saying the antiderivative is the function who I take the derivative of to get this other function, okay? It's really what it is. So, kind of keep that in mind. So every time you're calculating out an antiderivative, I want you to think of it this way, okay? Instead of thinking of these rules and things that we're going to learn on how to help us calculate it. At the end of the day, you're going to say to yourself, the function I have is the derivative of some other function. What is that other function? Okay? And if you think of it that way, you're going to have a lot easier time doing antiderivatives. Okay? A lot of times when people have trouble, they lose sight of that. They get caught up in these rules, and then disaster strikes. But really, this is what we mean when we're talking about an antiderivative. Any questions there? Okay. Now, integrals. What on earth is this integral? Okay. What do we mean by an integral? Oh, we got an email. Okay. Something important. Maybe. Probably not. Probably spam. Okay. For graduate schools. Okay. The integral is basically a notation used to describe how to do an antiderivative. Okay. There's two types of integrals that we're going to see. Indefinite, which is what we're going to deal with today, and tomorrow we're going to see definite integrals. Okay. We're going to start with indefinite. Okay. But basically, kind of notation for integrals is as such. It's this funky looking S symbol. In fact, it is an S. If you open up an old document from the 18th century, if you read the original Constitution, the S's would have been written like that. Okay, in the center of words. Okay, so that's an S. Okay, we'll go why it's an S later on, but basically integral symbol. Okay, f of x dx is equal to big F of x plus c. Okay, and here are all the pieces. This is the integral. Okay, this right here is something called the integrand. Okay, it's basically what you're taking the integral of. For the record, if you don't remember the term integrand, it's not the end of the world. It's like if you forgot. It's like if I wrote up a long division problem and said, point out what the quotient is, and you couldn't do it, but you know how to do the long division. Same sort of idea. Okay, not a big world. Obviously, big F here is the antiderivative. And then what we have right here is a constant added on, okay? And in fact, whenever you take an indefinite integral, okay, you're always going to have this plus c on the end, this constant added on, okay? And when you think about it, it comes about because, when I take a derivative, what happens to constants? They go to what?
No, zero.
They go to 0, right? So if I'm reversing that process, I should have these constants come back, but is there any way to actually figure out what the constant is? No, so we put it in as a placeholder as a plus c. We know it should be there, but we have no idea what it is. There are times actually where there are certain problems where you actually will figure out what the plus c is, okay? And it's usually because it'll give you some bit of information like x when x is 0, y is 5. Well, that's telling you the constant then is 5, okay? Things like that, okay? Yeah?
So that's the equation for the indefinite integral?
Yep, this is the indefinite integral. This is what it looks like right here. So I can come right here and say this is indefinite.
So the little s sign is the integral?
Yeah. This is simple for the integral. It's telling you I'm going to do the indefinite integral here. Okay. By the way, this is called an indefinite integral because there's no given interval of x, basically. Okay. So the difference between an indefinite integral and a definite integral, with a definite one, you'll actually be given a zone, essentially. You'll be saying, you're going to take the integral from 3 to 5, or from -2 to 15, or something like that, okay? When that's not given to you, okay, you have an indefinite integral. So there's no given interval, okay? By the way, if there is a given interval, the big change here is it'll be denoted with the interval will be written along the interval sign. So yeah, it will be from like A to B, so it'll be like from 3 to 5 essentially. Okay, and it changes what it's equal to in the end. Okay, what the answer is. So definite integral. In fact, actually, you don't have the plus c in the definite integral because it ends up going away when you actually calculate it out, but we'll get into all that tomorrow, okay? Any questions there? All right, good. So that's sort of the basics. This is what we're doing when we're doing an integral and an antiderivative. Basically, indefinite integral is essentially going to be synonymous with antiderivative, kind of from here on out. There's very subtle, slight differences, but when it comes down to it, if you're asked to find the indefinite integral, you're going to be calculating an antiderivative. Okay, and if you're calculating an antiderivative, just think, okay, we're talking about an indefinite integral. Okay, and working it that way. All right. So those are sort of the definitions here. Let's actually look now at how to calculate out indefinite integrals. Okay, so basic integration rules. Okay. The integral is, again, because it ends up being an antiderivative, it's the reverse of a derivative. A lot of the same rules for derivatives apply. Okay. Things like how to handle a constant, or things like factoring out scalars or Monda signs, okay, things of that nature. So, so those kind of carry over. The big difference, though, is integration is you don't have some of the same. There's not necessarily analogs to every rule that you have with derivatives. For example, there really isn't an integral quotient rule or an integral product rule, okay, like there was for derivatives. So remember, with the derivative, we have the product rule, or we have the quotient rule. And those don't really exist for integrals, okay. Likewise, there is an integral. There is something called a U substitution, which is the integral equivalent of the chain rule, okay. We're going to see that on a later date. We're not going to do that today. Today, we're going to keep it very simple, okay. Basic integration rules. The first one, okay, is that kind of the first one we're going to look at, is that the integral of a constant, or basically the integral of 0 is 0. Okay, because that's fairly straightforward, right? Next one, the integral of a constant is that constant times x plus c. Okay. So on and so forth. Okay. Next one, the integral of a function of two functions being added or subtracted, okay, splits apart just like derivatives do. So I can rewrite this as the integral of f of x plus the integral of g of x. Okay, you don't have to. So again, that's going to be useful. If you need to, you can split intervals up amongst different addition problems. Okay, those are some of the kind of the three basic ones. Kind of a fourth one. Minus signs and scalars can be factored out of an integral. Okay, so if I had the integral of a times f of x dx, I can rewrite that as a times the integral of f of x dx. There's you could factor them in and out without you could pull things in and out without question. Again, we saw all these basic ideas were also with derivatives. Okay, if I'm doing the derivative, I could separate it by addition or subtraction. If I have a scalar or a minus sign or something, I can factor it out, etc. Okay.
What would that a be?
A is a constant. Yeah.
In number 3, I understand like when equals the derivative, so it's the first part. So it shows you take the derivative of both when you break it out with the integral with each integral, right?
Yeah. You're going to do the integral of this one and the integral of that one. Okay. Just like you do with derivatives. Okay. Etc. So it's just again simple rules. We've seen these before. They work the same exact way. Okay. Any questions about those? Okay. The next one we're going to look at here is the first one for we're actually going to use to calculate out an antiderivative. And I'm going to call it the anti-power rule. I think the book calls it the reverse power rule, or a power rule for integrals, sometimes how you heard it called. Like anti-power rule. Mainly because it sounds very sci-fi that way. Well, it does. It's like antimatter or something like that. Okay. The anti-power rule. Okay. So the anti-power rule is just doing the power rule in reverse. Okay. So how what the anti-power rule would state is that if I have an integral of ax to the n, like so, when I take this integral, I'm going to add 1 to the exponent and then divide by the new exponent. Okay? So,
Do you not have one of those S symbols?
well, I'm actually doing the integral here. And the way I know that is I got the plus c on the end.
Do we always add then a plus c?
Yeah, for indefinite integrals, yes. In fact, I will fuss at you to no end if you leave off the plus c. Or I'll do what Mr. Fisher did to somebody and never use c around them until they got the message. So he was teaching an algebra class.
Oh.
Because they kept forgetting to put the c on the end. So he stopped using c's in conversation. Yeah. Or written correspondences. Okay.
It's funny.
Anyway, so but that's the yes. So the way I could tell why there's no integral symbol here is because I've taken the integral. Another way I know I've done that, there's the constant plus c added on the end. Okay. The third and final way is, remember, this is saying I got something that is a derivative of something else, What was the original function? What was that something else? Well, it's this right here. If I took the derivative of this, what would I get?
Antiderivative.
I'd get,
Oh wait, no.
if I took the derivative of the antiderivative, I'd get the original function back, right? If I use the regular derivative power rule on this, subtract 1 from the, multiply by the exponent, then subtract 1 from the exponent. Well, the n plus 1 over n plus 1 would cancel, and I have n plus 1 minus 1, which would leave me with ax to the a. Okay? And the c goes to 0. So that's always a way to check to see if you've gotten the right antiderivative, is to go through and actually take the derivative and see if it gives you the original thing back. In fact, it's an exercise you'll be doing later on this week.
So there's a, you could just do it that simple way opposed to doing the quotient rule for
Actually one.
But if you wanted to check it,
Oh yeah, well why would I use the quotient rule here? That's a constant at the bottom, n plus 1 is a number, it's like 5. Okay, and in fact, actually, here's what we're going to do here. We're going to take a look at some examples here, okay, of how this works. That way you can see. So, for our first example, we'll say, let's do the integral, indefinite integral of x cubed minus 4x, 4x squared, whatever, plus 7x minus 2 dx, okay? Well, anti-power rule, I'm going to add 1 to the exponent and divide by the new exponent. So, x cubed becomes what? When I take the antiderivative of it.
2x. Oh wait, no. 3x to the 4th.
Nope.
It's
Divided
x
by
over
3.
3, or x over 4.
X to the 4th over 4. All I'm doing is adding 1 to the exponent, then dividing by the new exponent. Okay? So x cubed becomes x to the 4th over 4. Okay? Think I'm going to reverse the process I used for the derivative. So for the derivative process, I multiply by the exponent, then subtract 1 from the exponent. So this process, I have to add 1 to the exponent first, then divide by that new exponent. Okay? That's how I get up here. So what would happen to negative 4x squared?
4/3 x cubed.
Okay,
over
so 4/3 x cubed. So minus 4x cubed over 3. If you want to write that as 4/3 x cubed, be my guess. Not a problem. Okay? How about 7x?
7 over 2 x squared.
Yeah. 7x squared over 2. Or 7 has x squared. Or if you really wanted to be fancy, 3.5x squared. Okay. What happens to the minus 2?
2x.
Yeah, it's just minus 2x. Okay? It's a constant, and the antiderivative of constant is constant x. Okay? And then, because I'm not done yet until I add it, plus c. Okay? Yeah, don't forget the plus c. By the way, on the AP, they will literally take off all points if you leave off the plus c. Okay? They will not give you any credit. I know, they're real.
Is it like who grades?
A bunch of calculus teachers from around the country. Dr. McRae wants me to apply and become a calculus grader.
Actually, you should.
I should. The thing is,
my
it's
exam and then you get
such a long way.
Do you get paid for it?
I don't know if you do or not.
Definitely get
I
paid
think
for it.
Yeah, you get paid in
Mr.
like,
McBride is on the
What's the motivation
environmental,
for it? You paid like-
board.
It's just it's good
$30.
career building.
Yeah.
Also, too, if you teach AP, you get to see the kind of the process from the inside.
that's helpful if you teach like the AP class.
If you go
And then-
grade and then you teach
When
it,
they
that's
grade them,
helpful.
they like learn.
Mr.
Yeah.
Kendall.
Yeah, because that's like Mr. McBride said he was on the original board of people that like founded the environmental science AP, so he knows
Oh,
all
okay.
the questions.
That's the thing, too. I mean, like even without grading, I already know what all the questions on the AP test are.
Why don't you just tell us?
I am.
No, you should tell us the exact number.
I don't know the exact numbers, but I know the exact question
You
types.
just find those.
Which is why we have the AP questions we do, which is why when we have a special theory, I write it up on the board and say, know this because and when we start getting actual AP prep, I will literally tell you there are 6 types of questions up here, and every AP free response. Here are the 6.
As soon as after spring break, are we going to start AP prep?
Pretty much. We might, depending on how far we get in this winter trimester, there might be 1 or 2 topics we still have to cover, but they're fairly straightforward.
What will the exam be like for juniors and Since we're not like doing.
last year what we did was we just gave you the same AP questions that were on the AP exam.
Oh.
So you had to second go of it, because they get released between time. I'll probably,
We won't cover much new material. will we?
yeah, we're not gonna cover anything. After the AP, what we'll do is we'll work on a fun project or something. Last year we did the disease model, which is the model of the Centers of Disease Control actually uses when like an outbreak occurs.
Oh, that's cool.
Yeah, it's pretty interesting. I also talked about how kind of geometry behind the global positioning satellites works. Okay, it's really fascinating how those things actually work, and it's part geometry. It's also part just timekeeping.
Yeah.
Like literally, all the satellite's doing is asking you what time it is, or rather, your GPS receiver is asking the satellite what time the satellite thinks it is.
Weird.
But it does that for several. It does that for like a minimum of 4 satellites, and so that satellite says it's this
Is it
time.
like a phone or like the computer?
And they can tell relative distance from the.
Yeah. And just by knowing,
So
by asking the time on each satellite. Okay. No, on your phone, what it's doing is it's talking to the various cell phone towers around, and so it's basically saying, okay, this cell phone tower is telling me one thing, this one's telling me something else, this one's telling me a third thing, so I must be here.
Because even when you don't have service, you still know that your phone still says the time.
That's because it's got a standard,
True that. Like a
Quartz
watch.
crystal.
That's really stupid.
like all computers do. Anyway, but
A
yeah.
watch doesn't have any service, but it's
So,
sorry, bro. What else doesn't have any service?
that's how an antiderivative works, okay? Any questions there?
So what else do you have to do after that?
Well, that's it, you're done,
Mark up.
okay? If you're looking for an indefinite integral, you're finished. If this was a definite integral, there'd be some minor changes, like we'd actually be evaluating this thing.
So I have to find common denominator.
No, you just plug in the number.
Is definitely integral like a point?
Yeah, would be over integral, but yes.
Oh,
Okay. So unlike derivatives, which are at points, integrals are over intervals. In fact, the integral and the derivative are really kind of the same thing. It's just one works for points, one works for zones. Okay. But anyway, let's look at another example of this. And the reason I want to do another example is because this one was fairly easy. The thing about the integral is, like the derivative, it really doesn't like things like radicals. The other thing too is oftentimes when you have an integral, you have to simplify it before you could go ahead and take the integral of it. Okay? So let me give you an example. Let's do this one right here. So we'll do 5x squared minus 2x over root x dx. We want to take the integral of this thing right here. Okay? Several things. First, when doing an integral, no radicals. You see a radical, immediately just change it back into a fractional exponent. Okay? It's just going to make life easier. Okay?
Should we make it
Second, this is a what?
rational?
It's a rational function. It's a quotient, right?
Bump that up.
Okay? So I can't, there's no quotient rule for integrals.
X and negative
Okay.
1/2.
But what I can do is bring that up as an x to the negative 1/2 and then multiply it through. Okay? Which is exactly how you would handle this. Okay? And in fact, you would rewrite this thing as the integral of 5x squared times x to the negative 1/2. Okay? Minus 2x times x to the negative 1/2. Okay? All that is still dx there. And the benefit here is, well, I'm not quite done yet. This right here, I'd have to simplify out. I actually have to multiply these through. Okay? But that should be fairly easy. What do you do when you multiply things with exponents? What do you do to the exponents? Add them. So I'm going to get, this becomes the integral of 5x to the what?
Wait, why'd you have to do x to the negative 1/2?
Yeah.
Sorry?
1.5.
1/2 or 3 halves. Okay? Why did I do it twice?
Yes, sir.
I'm bringing it up and multiplying the whole function by
Okay,
it, so
okay.
it distributes, okay? So 3/2 minus 2x, what happens to the exponent becomes?
1/2.
1/2. And now, we took the original function and we've now rewritten it in a form that we can do, okay? And so all we have to do here is regular anti-power rule, and we get our answer. So we get what, what's 3/2 plus 1? 5/2. So it's, and what's 1/2 plus 1?
3/2.
Why would
So-
the exponents of the new equation not be negative?
Because, when you bring that up, remember with exponents, when I'm multiplying things with exponents, you add the exponents together.
Oh, yeah.
Okay, so that's why. So if that had been a large enough root on the bottom, it could make one of those negatives. Okay, but as far as this is concerned, it just works out normally. That also means though, if I had a negative exponent with an integral, it works the same way. You just add one to it and chug along. There's only one that ends up being special, and that would be x to the negative first. Why would that be special? Because if I add 1 to it, what do I get? X to the 0th, which means it goes away, but it shouldn't go away, should it? No. So it ends up having a special, there ends up being a special rule specifically for it.
And then why is it brought up as x to the negative 1/2 instead of like x to the 1/2?
Oh, if it's down the denominator,
It becomes negative.
it's negative. Yep. So, and so this is our answer. Do I have to simplify that?
Nope.
Nope. Done. Okay. I can simplify it. That's actually fairly easy to simplify, but you would just be done with that.
Oh, I was wondering, how did you get like the 5 over 2?
It's mine.
Which one?
3/2 plus 1 is 5/2.
Okay.
Okay. 3/2 plus 1, or 2 over 2, makes it 5/2. Okay. That's how we get all those steps there. Okay. So that's how that works out there. Any questions? All right. Good. So, basically that's all there really is to this anti-power rule. Okay. We're going to learn some other rules later on, but for starters, we'll stick with that. Okay. Now what I'm going to go through here is we're going to look at a few special integral rules, and what these really are is, again, just kind of hammering home that when you're doing an antiderivative, you're saying, I've got a function that's a derivative, what is the derivative of? Okay, and basically, we're going to look at some of the common trigonometric functions and see how their integrals work. I'm going to write the derivative and compare it to the integral, okay? And so you see how the two basically are just the same thing going backwards and forwards, okay? I'm going to write them kind of not using the notation I was using before break, because remember, every trig function ends up being a chain rule, which means when you're doing an integral, it would be something called a u substitution, and we're not quite there yet, okay? But we can still do the basics. So for example, if I did the derivative with respect to x of the sine of x, what was that equal to? It's the cosine of x, right?
We'll do this.
Which means the integral of the cosine of x dx must be what? The sine of x plus c. Okay, good. Alright, and so you're going to see there's going to be a relationship there. Okay? Again, do the same thing with the cosine. What was the derivative of the cosine of x?
Minus sine.
Minus sine of x. So what's the integral of minus the sine of x?
Minus sine.
It would be cosine.
Plus c.
So what happens if you just were given sine of x?
Okay, well, if I was just given the sine of x, okay, I could, if I'm having trouble thinking about what that should do, I can add a minus sign to it by putting a minus sign here and then a minus sign out in front. Well, that I know, minus the sine of x goes to cosine of x, right? But if there's a minus sign out front, what would that make it? Negative cosine of x. So, the integral of the sine of x must be minus the cosine of x.
The minus is just a scalar of -1.
Basically, yeah. Okay? And so, and again, from that, from the fact that you can add minus signs and things, as long as you're not changing the value of anything, you can add all day long. So, kind of what I mean by that is confer. If I had the sine of x dx, I could rewrite that as minus the integral of minus the sine of x dx. Why can I get away with that? Two minus signs make a what? Positive. I know how that works, but then I have a minus sign out in front. Okay. Okay, so it's minus cosine of x plus c. Okay. Any questions about that?
Yes.
It's kind of a neat little trick you can do. Okay. And you get away with it because you're not changing, you know, the value of anything. I don't see that. There we go. Okay. So, what was the derivative of the tangent?
Secant squared of x?
It was secant squared of x.
Yeah, that's it.
So, here's the thing. I'm not going to give you, right now, the integral of the secant. The integral of the secant is something completely different, and it's weird. Okay, it's not something that you would like to see. However, I do want to illustrate that there is this relationship here. That if I did the integral of the secant squared of x dx, it should be equal to what? Tangent of x plus c. Okay? Again, this is something I want to stress. Whenever you're having an integral, always start, before you jump in and just start doing rules or start to think of anything special or anything like that, ask yourself first, I know this is a derivative, okay? What is this the derivative of? Okay? And if you can figure that out, you could very simply and easily solve these half the time. I can't tell you how many times I've seen students get this and be like, oh, secant squared of x. That means I must have to use this rule to it, and this rule, and that rule, and this rule, and that rule, and they end up just screwing the whole thing up. Okay? When really, it's like, oh, that's what it is? Okay, you should come out to that right there, and you're done. Okay? So, kind of keep that in mind. Okay? The other thing, too, is what you'll encounter as well with some of the integration ones here is some of those trigonometric identities you learned in pre-cal, you'll have to apply them here. Because you'll be given something, and on the surface it's like, I don't know how to do this, I don't have a rule for it. But if you think, okay, that means this has to be rewritten some way. Figure out how it should be rewritten, and then try to do the integral of it. Like, there's one on the homework, they ask you what's the integral. Not the homework tonight, but there's one in the book. Tangent squared of x plus 1 dx. What's that integral? Do I know how to handle that?
Yes, that's cotangent. No,
Not cotangent, but you're on the right track.
Secant.
it's one of the weird ones.
Not cosecant, it's
Secant.
secant. This is actually just secant squared of x. Okay?
That's a.
Plus C?
Oh, yeah. we learned
Because
that
it
last
comes
time.
from, it's a trigonometric identity. And then, so you had something which, by the way, if you did not know that trick, this is like impossible to do.
Yep.
Okay? But with the trick, we know it comes out to there, and then, well, what's that one? That's easy. Okay? So, it's that sort of thing you have to look for, or keep in mind, okay, when doing these. So the last three, I can go through and write them out. I'll go ahead and write them out because it's good review. What's it? Do cosecant first. I hate cosecant, by the way. So that means the integral of minus a cosecant of x cotangent of x dx is equal to the cosecant of x plus c. Derivative with respect to x of the secant. Is equal to secant of x tangent of x dx. Gives me over here CC. And finally, cotangent. Alright, and so there you have it, okay?
Can you go back up?
Yeah, definitely, okay. Kind of all the trigonometric relationships you would see right now, okay? Notice too, you can have variations on these, and again, it's just, you wanna just think through how these things should work. So for example, if I saw this right here without the minus sign in front, it would just mean that this here would be negative, okay? Things like that. So you want to keep that in mind as you do these things. Okay? Alright. Excellent. So, your homework tonight is going to be doing some of these antiderivatives, just getting used to calculating them out. And then tomorrow we're going to go over definite integrals and see how these relate to what we're after, okay?